approach to that. Why don't we go on? I think the next presentation then, in view of these circumstances, is my talk on how I'm going to spend my summer vacation. So let's get that up and we'll race through it. I'll start by saying that I have not given up on eclipses. I think occultations of eclipses, particularly timed measurements of Bailey's beads, have substantial promise in the future for monitoring the size of the sun. And the problem with what professionals do with measuring the size of the sun, they have several problems, I think, that are methodological. But apart from that, and I talked about that last year in a lengthy presentation I gave, but I think apart from that, the monitoring that's been done of the sun by professional astronomers is exceedingly expensive. And I just think they send up a satellite, the Picard satellite, and they're just not going to do that every 10 years. They're going to say, we know the diameter of the sun, and they're not going to want to do it anymore. But I think that timing Bailey's beads is relatively inexpensive, and it's something that can be continued for the foreseeable future by amateur astronomers who have this interest, and it may prove useful in monitoring the diameter of the sun. So how I'll spend my summer vacation is basically what I'm going to be doing a month from now. I am observing a 2016 eclipse from Tanzania. Next slide, please. This gives you an idea of the path from the Atlantic Ocean across Africa out into the Indian Ocean. Next slide, please. And this is where it crosses Tanzania, where the weather is likely to be best, and the maximum eclipse is right about here. There's a row of low mountains, high plateau across Tanzania here, and this area is a desert this time of year, and it's brush and so on, kind of like New Mexico, and I think that that'll be a good place to observe from, and Paul Maley has arranged an expedition to that area, and everybody's going to the center line about here except me, and I plan to be right there. Now, next slide, please. Now, this is the same as the last slide, except I've superimposed in blue the areas of Tanzania that have lions. And now, I happen to have a picture of an astronomer with 2 lions. Next slide, please. This is an astronomer with 2 lions. Next slide, please.
Which one's the astronomer? They don't like lions.
All right. Well, it's about a 97.5% eclipse, and I think they measure that by diameter, they measure that by total sun occluded. I don't even know. I saw the figure 97.7%. It gets pretty thin down here, and it really doesn't project well, but if you look at the original slide, you can see there are some bright points along there, and those are Bailey's beads, but that's what it's supposed to look like at maximum. It'll be yeah, it's going to be a southern, I'm on the north edge of the path, which means I'll see the beads on the southern edge of the moon. Okay, next slide, please. By the way, that picture was from the Occult program, which has a wonderful set of programs that predict and analyze Bailey's bead phenomenon eclipse. Now, this is a picture from the last Venus transit, and I'm not showing it for the transit. Obviously, there's Venus up there. I'm showing it because you notice that the center of the sun is brighter than the edge of the sun. This is called limb darkening. Next slide, please. And at the top here, we have a brightness curve across the sun, and if you look carefully, you can see at the edge, it's almost vertical, and it actually has an inversion point. If you measure the slope of this, and the slope peaks, and then it levels out, and it peaks again at the edge, and where the slope is steepest, they would call that the inversion point, and that's the point where they say the edge of the sun is, by definition, is that inversion point. And I've forgotten the number. Richard rattled it off to me at lunch. I thought it was 967 points something arc seconds is the radius.
That was close to like 959.
Yeah, something like that. Okay, next slide, please. All right, well, this is my diagram. If you imagine this is the edge of the graph we were just looking at, where the limb darkening effect causes this vertical look at the edge of the sun. What you get is scattered light at the edge of the sun. So when they image the sun, the inversion point is presumed to be scattered light. And remember the abscissa is going outward along the radius, and brightness is the ordinate here. Next slide, please. Now, if you have a sensitive camera with a very low black level, you can see the scattered light, and you can see way out to the edge of the sun. Next slide, please. But if your camera is really sensitive and your black level is really low, you should be able to see the chromosphere. Well, guess what? None of the professional measurements of the diameter of the sun show the chromosphere. They show a black background at the edge of the sun, and nothing but scattered light is what they measure. Next slide, please. Now, when I did a bead observation, this is from 2002 in the Outback, we got a nice fall off in light, and this is the Bailey's bead declining in brightness with the frame advancement, and it curves down here and it sort of tapers off, but look, it continues to decline very slowly. You could say that maybe it levels off way out here, but there's a long decline. And on this graph, when you look at the video, it's obvious that there's a faint glow that you can still see. That's the chromosphere. And some of this is Bailey's bead, and some of it is the chromosphere, and there's no clear dividing line in between. Now, this is what I want to study. I want to know where the edge of the sun is, okay? Now, the way to tell that is, I think, the best method I know of is with spectrum, the spectrum of the Bailey's bead, and that's what I want to try to take a look at. Next slide, please. Now, the problem that the professionals have is this. They have a high black level. They're way up here. Everything below this line is black. They can't see the chromosphere. They're not even see the scattered light I see on my Bailey's bead images. They can't see it. It's too dark. They've got scattered light up here, you see. There's always scattered light, but for them the scattered light is just enhancing the brightness right here, and there's an inflection point up there, you see. Next slide, please. So the difference in the measurement of the radius of the sun due to camera sensitivity is this. The professionals don't have a sensitive camera because they can't. Otherwise, they can't see the limb darkening. If their camera is sensitive, they can't see limb darkening. They'll have nothing but scattered light. It'll be way overexposed, like my mighty mini view of the moon the other night. And so, you know, only by blocking out the sun can I use, with the moon, can I get an inflection point way down here with scattered light before the chromosphere. And I see them both, you see. And so I'm much closer to the limb of the sun than the professionals are. But how do I know where the actual edge is? How do I know where the chromosphere becomes brighter than the sun? I know because the chromosphere has an emission spectrum and the sun has an absorption spectrum. Next slide, please. All right, I'll try to race through this. This is sort of a cross-section of the edge of the sun. This is the body of the sun, and the photosphere is about 400 kilometers thick. It's not just a layer. And then we have the chromosphere above the photosphere, a transition region, and these are spicules. They're parts of the chromosphere that protrude into the corona. The transition region is a couple hundred kilometers thick, and what it's well known for is a rapid rise in temperature. This graph, this white solid line, is the temperature of these various layers, and the transition region rises very rapidly into the corona. But notice that by the way, this is a logarithmic temperature scale. The temperature declines as you come to the exterior, and the low point in the temperature is about a third of the way out into the chromosphere. And then it rises again, and in the upper half of the chromosphere, the temperature is about the same as it is in the photosphere, which means that light is bright. I mean, it's the same color as the photosphere. The difference, however, is that this is much less dense, and that makes it too faint to see. It's so, what do I want to say? It's not tenuous, great word, tenuous, so it doesn't cast much light. So it may cast a faint continuous spectrum. Meanwhile, down here, we get absorption from the brighter photosphere beneath, and so this absorbs at certain wavelengths, and that creates an absorption spectrum. So the photosphere is masked by the absorption in the chromosphere above it. So if we're seeing the chromosphere without the photosphere, we'll see an emission spectrum as it emits at those wavelengths. I'm sorry if I'm saying it backwards. You know, I'm just trying to talk fast. But if we can see the photosphere, it so overpowers the chromosphere that all we see is the spectrum of the photosphere, which has an absorption spectrum. Anyway, you get the picture. Next slide, please. Yeah.
So are you going to look at dark line versus bright line?
Yes. Next slide shows that.
Okay.
This is made by Campbell in 1906, and he took a gradient filter, and put it across the edge of the sun, and he actually noted that this is what the solar disk looks like. Near the limb, it looks somewhat different from how it does in the center of the sun, but as you get, there's a dark line over it. Look at that dark line. That's the edge of the sun. Okay? And right about there, we're getting transfer. The dark absorption lines of the photosphere disappear, and the bright emission lines of the chromosphere appear, and there's a little bit of cross in between them. But the point is, you can get some idea of where the edge of the sun is by the transition between the absorption spectrum and the emission spectrum. But you see, it's not all that distinct. Nevertheless, we need to have some idea of what we're looking at, because for all we know, Bailey's beads are the lower chromosphere. They might be the inner chromosphere. We don't even know where the line is. We need to try to document that so we know what we're looking at. Okay, next slide, please. You see, in our eclipse measurements, we have gotten diameters of the sun that are slightly greater than the diameters that the professionals have obtained. One of the reasons is, as I showed you, they're not seeing the edge of the sun because their camera isn't sensitive enough, because if they use a sensitive camera, they overexpose the sun, and so they, you know, I went through all that. The point is that we get a bigger diameter. How much of that is actually what we think it is, and how much of it is due to being misled about where the chromosphere is? Okay. Anyway, this is a star spectroscope. This is a part for visual use you put over your eyepiece. I won't be using that. This is the part you screw into your C-mount, you know, for your video camera, and it has a blazed grating. Now, that means it's not just an ordinary diffraction grating. They blaze it with a laser, and what they do is they make it so that it's not just lines, it's actually Z-shapes, you know, and so on. And it actually scatters the spectrum so that only about 20% of it goes to the zero order image of the bead, and the first order spectrum is going to have over 70% of the light. And the way that's designed, it actually first order spectrum bright on one side and almost negligible on the other side of the zero order. So the point is that this is designed specifically to show the spectrum by transmission, and it's actually quite efficient. Next slide, please. This is the kind of thing I want to do. I expect to only have 2 telescopes. I'm going to be using, I hope, the 2 larger ones here. This is a C5 and this is a 95 millimeter Maksutov. This actually that's me, by the way. Notice when I use the multi-scope setup and you want to fly on airplanes, you don't carry counterweights. You take a hiker's bag and you fill it with water, okay? And things like that, and you rent a car and you run it all off the car battery, and I was clouded out in Panama. That was in, I think about 2005, wasn't it? Yeah. Next slide, please. Yeah, we had fun. Coffee, man, it was good down there. And what else was good down there? A few other things. Flowers, wow. Anyway, I just want to, I think this is my last slide. Oh, it's not my last slide. You didn't update my program. That's all right. You got the one that I didn't update. But I just wanted to show you the type of data I got when I got good data in California for the eclipse in 2012. Annular eclipses versus total eclipses. Let me just say firstly that from the standpoint of looking at the beads, an annular eclipse is just as useful as a total solar eclipse. Now, what is the difference logistically in going to an annular eclipse? Here's the advantage. 100,000 observers come to every total solar eclipse. About 1,000 go to an annular eclipse. That means there's room in the hotels, you can find a rental car, you know, stuff like that. It's really important. And so if you're interested in Bailey's beads, don't miss the annular eclipses, okay? Anyway, but if you're gonna, which limb do you observe? If you're observing a total eclipse, if you're on the north edge of the path, you need to look at the north limb of the sun, at the moon, you know? If you're on the north edge of the path, then on the north limb is where you'll see the beads. But guess what? If you're on an annular eclipse, you better get this right. If you're on annular, if you're on the north edge of the path, you've got to look at the south edge of the moon. Okay, that's the geometry. All right, and if you're on the south side of the patch, you look at the north edge of the moon. All right, and if you want bigger beads as you're planning this, you say, now wait a minute, those beads, they're not very impressive. If you want to make the beads bigger and you're planning where you're going to set up, on a total eclipse, you go away from the center line and the beads get bigger. On an annular eclipse, you go toward the center line. Okay, and where do you look? Well, in a total eclipse, the moon's bigger than the sun, and the moon's leading edge, before, as it begins to cross the sun, its leading edge will show the beads first. And after central eclipse, the moon's following edge will show the beads. But guess what? It's exactly the opposite at an annular eclipse. And you can really miss a lot of data if you do it wrong. So you want to know that you're not only on the south edge of the path for a north limb eclipse, but you're going to start looking at the following edge of the moon, and you'll finish the eclipse looking at the leading edge. Okay? So just so you know all that in advance and plan it, because believe me, you can't do any planning at the time of the event. Okay? And the only other thing I want to say, if this sounds interesting to you and you think you might want to do it someday, which I would certainly encourage you to try, it's a great adventure. Not only do you have to plan, there was something, understand that focusing at an eclipse is a great challenge. By far, the biggest problem I've had at eclipses, again and again, is half my telescopes will be out of focus. Okay? I mean, it's just so hard to focus at an eclipse. The sun, the edge of the sun, you don't see any detail on the sun, you just see the edge of the sun, and you just have to, you see that little cusp, you know, you just try to focus on it. And it's really hard to do it accurately, very challenging. Did we ever find the other slides that I gave? I gave you an update with 2 more images. I guess we don't.
Yeah, I don't see it.
Okay. Why don't you go to, is this the last slide? I thought I stuck them in the middle and we just missed it.
Yes, that's the last slide.
Okay, so, yeah, well, we won't show the others. We're too far behind. Okay, any questions?
Roger, you have to worry about how you orient your grading.
Yes, correct.
It's not going crossways.
That's right.
Do you have to keep it out of the sun, or does it matter if it's going into the, or the moon, I should say?
Yeah.
Or, no.
Steve Conrad is pointing out that I need to pay attention to the orientation of the grading. That's exactly right. I need to practice on stars. You know, you can use it at night without a solar filter, and practice and mark the grading as to exactly which way to turn it, you know, with my actual setup of telescopes, so I know exactly which way to orient it. And of course, what I want to do is have the spectrum projected at a right angle away from the body of the sun. Okay, and so the 2 telescopes will have slightly different pointings. One of them will be pointing to centralize the beads and image the beads, and the other will be pointing to centralize the spectrum. and image the spectrum. Okay. Yes.
Use any kind of a solar filter on the front of the strip.
Yeah, I'll be using, for the Bailey's bead, I'll be using two filters. The first is a full aperture filter on the front of the telescope of neutral density 3.8. Now that's a photographic density, not visual. Actually, you can look through it, but the sun appears almost painfully bright. It won't damage your eyes, but it's a neutral density 3.8 made by Bader. And then I'm going to be using in front of the video camera a color filter in green at 500, centered on 550 nanometers. Now the reason for that is that that's for what we call photoptic vision or daytime vision. The maximum sensitivity of human vision is at 550 nanometers. And this will have a 10 nanometer full width half maximum bandwidth. And so the reason I need the neutral density 3.8 instead of neutral density 5 that most people use is because I'm cutting out further light with the color filter. And I've already tested this in California, and that's the other thing I wanted to show you. I had a really good slide of Bailey's beads made with a 5-inch telescope at an annular eclipse in California with just that same set. I'll be using the exact same equipment for that.
550 nanometer narrow band with a 10
nanometer
width.
Yeah.
Narrow band.
Full width, half maximum bandwidth.
Yeah, right.
Yeah, right. And then
Bader makes a good
yeah, and for the other telescope, I'll probably use the 95. Haven't decided which one I'm going to do with what. Maybe I'll be using the 95 millimeter for the beads. But anyway, I'll have a neutral density 5 filter, and so it's going to let through more light, full aperture solar filter. And then I'll be using the spectrum on that and pointing it so that the spectrum is in the center of the video field. Okay.
And that last question, that wavelength is suited for
That's all.
chromosphere?
Yeah, that's full wave. There's no wavelength cutoff on that. That's integrated light. Okay. Yeah.
Very interesting.
Any other questions?
So is anything to be gained by going to one of the highly ionized iron wavelengths in the...
Actually, the iron wavelengths, as you look at them on the spectrum, are mostly fairly faint compared to, say, the sodium D line and the A, B, C, D, E, F, H and out to HK, that Fraunhofer originally identified. Those are the really intense lines. The problem is that the ones that are bright in the chromosphere are the red end. So, and they're going to be farthest from the zero order. They're diffracted way out to the side, and so I have to point the telescope so that I'll see the red end of the spectrum in order to have maximal sensitivity to the spectrum to ascertain whether the spectrum is emission or absorption in character. And so I don't expect to see the H and K lines of calcium very well because that part of the spectrum from the chromosphere is very faint because it's red. The chromosphere is cooler, and so it's redder, and I'm not going to see the violet end of the spectrum very well over there. Okay. Any other questions? All right.